Hello, I'm Frederick. This is a joint work with Nima and June. And this is about trickle down in localization schemes and applications. Okay? And so I thought I'll start off just by hitting you with the quick summary or the TLDR. Okay, so here's my quick summary. Oftentimes, if you're some kind of mathematician, you want to show that some geometric object is well connected. And Oppenheim's trickle down, which apparently is an application of something called Garland's method, according to Oppenheim, is an inductive way to show that a simplicial complex is well connected. So if you don't know what a simplicial complex is, it's basically just a geometric object. Okay, and we're going to discuss the precise meaning of this soon. And although maybe you don't know what a simplicial complex is, or you're not sure why you care if they're well connected, it turns out this had a lot of applications for things like, for example, sampling spanning trees or edge colorings in graphs. So perhaps if you care about those things, or if you care about like log concave polynomials, geometric polynomials, it seems that this trickle down is extremely important. And so what did we do in this work is we thought about trickle down and we generalized it to what are called linear tilt localization schemes and used it to prove a bunch of new mixing time and concentration of measure results. Okay, so that's the TLDR. If you want to stop playing the video now, I won't be upset, don't worry. So the way I'm going to structure the rest of the talk, I'm going to tell you more about trickle down. So this is not really it's not the contribution of this work, it's like the previous work. But it's interesting and it maybe takes a little bit of time to become intuitive. And then I'll tell you a bit about what we did, and that'll be the talk. The story about all this like high dimensional expansion stuff, it just starts with, start with graph theories, okay? And in particular, also in Markov chains, we want to understand these questions like, okay, geometric object is well connected, and like a natural intuition, especially in those areas, is that like, what it means to be well connected is like you can explore the space very easily, okay? And this is a much more precise kind of definition, is that a natural random walk will be rapidly mixing, and rapidly mixing just means you forget where you started very quickly, and you converge to the so-called stationary distribution. Okay, and when you study this kind of rapid mixing properties, they end up to be equivalent to certain type of isoperimetric inequalities. Okay, so isoperimetry, the sphere, it's like optimal for the surface area given its volume. And in general, when we say we want to look at isoperimetric inequality, I guess usually it means something like that, like every large volume set has a large surface area. Okay, and it makes sense that like this would, or hopefully it seem a little bit intuitive that this would be related to being like well connected and rapidly mixing, even though the precise connection I haven't stated yet. Okay, and in graph theory, this leads to the concept of a so-called spectral expander. Okay, and so let's just for fun define what is an expander, spectral expander. Well, you have a graph. There's a natural random walk where you are at one vertex, you pick one of your neighbors uniformly at random, and you walk to it. This is in the case that it's a deregular graph. For non-deregular graph, there is of course a natural random walk, and actually it arguably makes more intuitive sense if you think about it's like you're an edge, and then you pick one of the two vertices you're next to. So we'll see this perspective later, but let's say we're in a deregular graph. You pick a random neighbor and you move to it. Sorry, that definition also works for non-deregular graphs, just what are the stationary changes, okay? And like I said, let's consider the deregular case. And then it turns out spectral expansion is very easy to define. Be a spectral expander if the second eigenvalue of the normalized adjacency is not too close to 1. And then like by the power method, this sort of means that after not too many steps, A is going to be very close to its top eigenspace, which is the stationary measure. Okay, and we also call this relaxation time. And kind of a couple canonical examples. The complete graph, that's really the best expander. In one step, you kind of almost completely forget where you started because you'll be uniformly at random among all the other vertices. If you make the walk lazy, you could even make it so that it mixes completely in one step. Sparse random graphs are also very good expanders, which so like just rainy graphs with sufficient density, random deregular graphs. Those are great expanders. Things that are not such good expanders would be things like, for example, a path or two cliques connected by a long path. And the basic problem, for a path is that the left and right ends of a path are far from each other. So unless you take, clearly unless you take at least like n steps, you cannot move distance n, right? And in fact, because of randomness, like you'll need even more steps than that. So you really cannot explore a path without taking a while to walk around. And then high dimensional expansion was this idea, which has different forms. But let's talk about spectral high dimensional expansion. It generalizes in a natural way expansion of graphs to higher dimensional objects. Okay, so a graph is like a set of edges and vertices, so that's a one-dimensional simplicial complex. In general, we could view a simplicial complex as a collection of sets of size k plus 1 if it's dimension k. So graph edges, they have two elements, their dimension is 1. Okay. And you can kind of think the thing after edges are triangles. Triangles, they have three vertices. They're two-dimensional. Then there's like actual simplices, which will have, like 4 triangular faces, and then those are three-dimensional, and you just keep going up. So that's what motivates this definition. And then, you can just define spectral expansion in the same way. You want random walks between faces and vertices to mix very rapidly. And all right, here's the key thing. The trickle down says that when you look at the set of faces, which have all but 2 vertices shared, and you look at the restriction of the walk among these faces, so in this case, it's like you're going to be at a face, and then you're going to walk to another face, which, you're going to be at face, you're basically going to drop one of the vertices that's not required to be there, and then you're going to add in another one of the vertices that's allowed to be there, and see what face you end up at. Okay, so maybe the picture is more helpful. If you look at natural walks on the faces that are kind of next to each other, and those are really, really good expanders, like those walks makes really, really fast. Then Oppenheim was able to prove by a clever inductive argument that this means that high-dimensional versions of these walks mix very rapidly. And more precisely, the walk that he analyzed corresponds to, you have a face, you drop all but one of the vertices on this face, and then you go back to a face which contains this vertex. And that's called the k-to-1 up-down walk, or down-up walk. Okay? And so, this is exactly what I wrote. So there's a down step. You start at a set S. You go down to a vertex I. And there's an up step where you sample from the posterior, given that their down step led you to this vertex. Okay. There's also a k to k minus 1 walk. But even if that's what you care about, the k-to-1 walk is what trickle-down studies, and trickle-down is like the key thing that makes so many amazing applications work. Okay, and this is kind of like a pictorial story about trickle-down. Basically, trickle-down says, okay, if you locally you're like really, really good at expanding, then your high-dimensional object is a disjoint union of high-dimensional expanders. And it's an important thing to think about. Like locally, you can't really tell if you're connected, right? So if I were to say, being locally well connected means you're globally well connected, it's like clearly false. Because imagine you have two, like Earth and Mars, and Earth is very well connected and Mars is very well connected. You can't tell from the local properties that, these are actually two separate places that you can't get between. But the amazing thing about trickle down is that except for this obvious counterexample, it's actually true. Okay. This is a formal mathematical statement. It just says there's an inductive relation between the spectral gap when you require certain vertices to be in your face, like I was saying before, or condition on them, and you start with conditioning on a bunch of them, and then you condition on less and less until you get back to the original complex. And it's just an inductive relation between these the spectral gaps of these walks. Okay, and then an important example was in spanning trees. The vertices are the edges, the faces are the spanning trees, and you can walk between these. Okay, I'll skip the analysis of this, but yeah, you end up just studying some kind of not super hard spectral gap theory question, and then you use trickle down, and just oversimplify a bit, like those are the key things that let you prove that the down-up walk on spanning trees is rapidly mixing. So this was proved by Anari, Liu, Ovis, Garan, and Vincent. Okay, so now that we kind of had like a rocket speed overview of trickle down, let me tell you about trickle down and localization schemes. Okay, and yeah, of course, please, you can look at the paper if you want to have a less rocket speed version of everything. But yeah, here's kind of the question is like, how can you generalize this idea that local well-connectedness yields global well-connectedness to other settings? So for example, if you operate on continuous spaces, we tend to use like continuous random walks, like the Langevin dynamics, for example. It's not really clear how that, for example, relates to the story about simplicial complexes, but there still are random walks on natural geometric objects, so you would kind of hope that all of these things are kind of related, okay? And so this framework called linear tilt localization schemes is this nice definition which kind of lets us actually generalize these things. So, okay, quick summary. What's a linear tilt localization scheme? It's just like you have a measure and then you keep reweighting it in this random way. So you have a martingale difference sequence. And yeah, you start with nu t and you define the density of nu t plus 1 over nu t by the inner product of x minus the mean dot product with this new guy in the martingale difference sequence. So it's just like a mathematically precise way to say I keep reweighing by linear functionals in a random way. And this, the martingale property is like really important for, when you take the expectation over z plus 1 here, you're going to get 0. So this is going to tell you that the total mass of the probability measure stays to be 1. So that's kind of like the intuition. Okay, and also being a martingale is going to guarantee that the sequence of random measures is a martingale. Sorry, that's actually where the difference property is used. Okay. When you take the average over x, then the x and the mean cancel, so that's why it stays mass 1. Now, the key point is that this can kind of generalize the idea of pinning vertices beyond the original context of simplicial complexes. Okay, and so here was the story for simplicial complexes. You basically start with a uniform measure over the faces, then you can kind of generate a sequence of random measures by picking random vertices and then requiring only looking at faces which contain this vertex. So you condition on that vertex being present. This is what the picture illustrates. This is called looking at the link. So that's a terminology from topology. And in statistical physics, you call this a pinning. Okay, so we use both of those terminologies. Okay, and so this is the idea is that all of this framework for high dimensional expanders is built on this idea that basically you want to structure your induction this way where you have a sequence of measures that are getting more and more local, and then you kind of that's how you relate to global and local properties. Okay. And now, what we can do is that once we think about this actually, and with a sufficient understanding of trickle down, you realize that trickle down is actually this equation which tells you how the covariance of this sequence of measures are related, and you can just state this in generality. So that's what this equation is. It follows from the law of total variance, which is kind of the only way you can imagine to prove something like this. And the significance is not that, the law of total variance is true, which of course we know is true, but maybe the really important thing about trickle down is it realizes that it's actually very useful to take this perspective. And I think that's the thing which is difficult to intuitively explain. but yeah, it has to do with this story about like local connectivity yielding global connectivity. That's like the heart of trickle down is like you can do this and it will actually work in a lot of settings. But like yeah, from a down to earth perspective, it lets you control a covariance of the measure at time t, which is the stuff on the left hand side of the equation, by the covariance of the stuff at time t plus 1. And so if we think about the localization is happening forward in time, trickle down is going in the reverse direction of time and controlling the covariance measure. So we call it backwards induction over time. Yeah, and like by doing linear algebra, you can start with this covariance equation and you can recover trickle down. One of the key things you need to know here is that high dimensional expansion actually is the same thing as an upper bound on the covariance matrix, which again can be proved directly from linear algebra, but I think not everyone was necessarily aware of this, although it is, yeah, it has been known for a long time. Okay, so yeah, this is just from our paper. You know, rephrased in this language, you can reinterpret Oppenheim as the upper bound on the covariance matrix, which is proved with this equation. And now, yeah, I promised some applications, so let me tell you just a little bit about the applications and how they work. Due to time constraints, I'm not going to go into the details. But yeah, I think the idea that, oh, we should take this trickle down from simplicial complexes and then apply it to all these other settings. Yeah, I really think that was like the core idea which enable all these applications. Although, of course, you have to do a bunch of work, you know, to actually make the idea work in each application. And so, yeah, one of the applications was in the context of spin glasses. So this is a great article I found online which explains why spin glasses matter. So maybe, you know, since I don't have much time, you can look at this article. The spin glasses basically originally are metallic alloys where spins like to align and disalign, and this creates frustration. And spin systems were also used to model the way that birds fly. You know, the direction of one bird and a bird next to it is quite correlated. And this is actually like a similar kind of statistical physics model that you can use and was successfully used in biophysics to model these things. Okay, so very quick summary. This one is kind of not frustrated. They actually like to align. So, okay, there's a tiny bit about statistical physics. It's had some very impressive applications. Okay, and now one thing we can do is we can go back to these statistical physics models and try to rigorously prove some of the things which are widely believed to be true. And one thing is that it's widely believed to be true, and I think kind of considered trivial in some sense to physicists, that Glauber dynamics will mix rapidly in the standard or the most basic spin glass model, the Sherrington-Kirkpatrick model. So this is a probability measure which looks like this. It's basically a one where your log likelihood is a random quadratic polynomial. It's a distribution over the hypercube. And Glauber dynamics or Gibbs sampler is probably the most common way to sample this kind of thing. So you pick a random site and resample your spin at this site conditional on everyone else, okay? And like I said, it's believed that in some sense that this is rapidly mixing whenever beta is less than 1, and that this is kind of clear. But then, yeah, you can think from a mathematical perspective, proving isoparametric inequalities, kind of tricky, mixing time, kind of tricky. So we really don't know this. And best previous results is that when beta is at most 0.25, so beta is like the scaling, how strong the interactions are, it's called the inverse temperature. We could prove this up to 0.25. Now, what we can do is we can get up to 0.295. And one thing that makes this interesting is that this actually 0.25 is the sharp threshold for some notion of log concavity of the measure. So this kind of tells us that the convexity is actually not the thing that really determines, in this case, when it's rapidly mixing. Although, yeah, we don't know what exactly the sharp threshold is rigorously. Yeah, maybe I can say very little about, how do you get this improvement and where does this concavity come from? The original trick was like you can add noise to the measure and it gives you a log concave distribution up to 0.25. It uses these old ideas to do Hubbard and Sirtanovich. It's called the Hubbard-Sirtanovich transform, and this was used in a paper by Braskamp and Lieb in the 70s. And then there was a lot of nice work recently, starting from Bauerschmidt and Boudinot, that was revisiting this idea and using it to prove structural properties of the measure. And it's not really specific to SK, but holds whenever your interaction has a bounded operator norm. And what we realize is that although, okay, there was all this trick before, it's very clever, and it's actually sharp in some sense. This threshold of 0.25 is sharp for kind of a worst case model. You can look at more precise properties of the spectrum of the interaction matrix instead of just looking at its operator norm. And in particular, when the spectrum is symmetric, we can get improved bounds. And that's the case in the SK model. Okay? And it's not that we decided, let's look at the shape of the spectrum, and then obviously that leads to a better mixing. But it does naturally show up when you try to analyze these trickle-down equations. Okay? I don't have time, unfortunately, to explain the proof via log concavity. You can see it fits on one slide. But yeah, trickle-down helps us recast this story as one about stochastic localization, which is a well-known process. It's a well-known example of a localization scheme. And yeah, you can kind of recast the previous story as being not a very sharp way. You can first reprove it using a trickle-down perspective, and then you can realize that proof is not very sharp. And then with some more work, you can figure out a sharper version. What happens has to do with anti-concentration. That's, again, in some sense, pretty elementary, but also not really something that I think, it takes a little bit of effort to explain, but it naturally shows up in the trickle-down. Okay, we get a bunch of curves which basically improve the previous result. You can also do it for continuous models. You get a bunch of curves as well. The trickle-down kind of naturally leads to these kind of integral or differential equations, which you can just solve with Mathematica and lead to improved bounds. Okay, there's also an important application, last thing I'll say, to anti-ferromagnetic easing model and expanders. So yeah, you can come up with a dynamics which mixes very rapidly, and then it uses this really cool idea called polarization from stable polynomials and log concave polynomials, and again, the proof combines that with a trickle-down analysis. Okay, I have to skip this. This is a diagram of how the proof works. You can read the paper, and that's all I have time to say. So thanks for coming. I hope I whet your appetite for this work. Okay, thank you.